Hey Tina, what are you doing?
Testing out this new light bulb demo I just built to show how efficient LED light bulbs are compared to the old style.
That's cool. Can I try it?
Yeah, there you go. All right, crank away. So you're gonna start cranking on a 3-watt LED light bulb. Pretty easy, right?
Yeah, that's real easy.
Now I'm gonna kick on 25 watts of the older style.
Jeez,
Pretty hard, right?
that is tough.
Yep, that's 10 times the power almost.
Man, imagine how many people it would take to power the United States at 500,000 megawatts of peak demand. Good thing we have power generation stations to take care of that.
Heard that.
How do we generate the electricity that is used all over the world today? There are many different forms of power generation being used, including the burning of fossil fuels, nuclear power, and renewables. Today, the majority of our electricity is created by burning of fossil fuels, primarily coal and natural gas, to spin turbines that are connected to an electromagnetic generator. This is changing as renewables and natural gas are becoming more cost-effective. Utilities produce this energy inside of large power plants, also known as generation stations. Let's start with the question, what is a generator and how does it work? A generator converts mechanical or kinetic energy into electrical power or electricity by electromagnetic induction, which is simply varying a magnetic field within a coil of wire. This phenomenon is explained by Faraday's law as shown here in this example. As that induced current travels in a loop on the wire, it will create a magnetic field. Because the field is continuously changing or alternating, it creates what we would call a sine wave or alternating current waveform. Historically, the first generator invented was a direct current or DC generator called a dynamo. DC power produced by these generators was limited because the generation source had to be close to the loads. Then came alternating current produced by AC generators called an alternator or a synchronous generator. The major advantage of the AC generation is that with transformers, the voltage levels can be changed up and down to transmit that power far distances to the loads that require it. So, how does a generator work? The two main parts of a generator are the rotor and the stator. The rotor is the part that rotates and consists of many loops of copper wire or bars called field windings. Field windings are used to create the magnetic field induced on the metal core to which the wire is wrapped around. The stator is the stationary or static part of the generator that consists of copper windings called armature windings. The power that is produced by the generator will flow out of these armature windings towards the load. Let's get a better understanding of the basics of how the rotor and stator interact to generate power. First of all, we need to understand that the rotor spins inside the stator, and one full rotation is equal to a complete cycle of power. In North America, this would equate to one 60 Hertz cycle. For a generator to produce power, an electromagnetic induction must occur between the field windings in the rotor and the armature windings in the stator. A magnetic field must be created in the field windings on the rotor. Traditionally, this was done using permanent magnets, but with larger scale generation being needed, electromagnetic field coils were able to produce substantially more power. This is done by applying a DC current or excitation current to the field windings through a pair of carbon brushes and slip rings. Slip rings are attached to the shaft of the rotor and spin with the rotor, while brushes are stationary and connect to the end of a wire with a spring pushing on them against the slip ring, making an electrical connection. The field winding is a continuous wire that is looped around a certain number of poles that are part of the rotor core, with positive polarity connected on one end and negative on the other. North and south poles will be created depending if the coils are wrapped clockwise or counterclockwise around the poles. This essentially is creating an electromagnet with the DC source. This DC current can come from an external source or from a small exciter rotor with a rectifier that is attached at the same shaft as the main rotor and is called self-excited. This excitation current is a crucial part in the voltage regulation of the generator. The magnetic field strength of the field windings on the rotor can increase or decrease by changing the amount of excitation current. The amount of current and the number of turns in the field windings determine the strength of the magnetic field. The control of the excitation system allows the generator to maintain voltage, control reactive power flow, and assist in maintaining power system stability. During load changes or disturbances on the system, the exciter must respond, sometimes rapidly, to maintain the proper voltage at the generator terminals for the load. The two common types of rotors are cylindrical and salient. Cylindrical will generally operate at speeds of 1200 RPM or more, and salient at speeds below 1200 RPM. So, we know how the magnetic field is created on the poles of the spinning rotor. Now let's see how the field transfers onto the armature windings or poles of the stator and turns into usable power. The stator is enclosed inside a metal housing and consists of two main parts: the outer part of the stator, called the core, and the armature windings. The core is generally made of a low-loss magnetic material and used to support the coils of the armature windings, and is also a return path for the lines of magnetic field. The magnetic field created on the rotor induces a current onto the armature windings. The stator windings tend to be larger, highly insulated, and more complex than the field windings in the rotor because they must carry the generated power through them that is of a much higher voltage. A three-phase stator will consist of 3 windings, where for each phase there is 1 group for each rotor pole. Each group is interconnected and can be considered as one large coil. Each group has an output lead from a generator that is 120 degrees from one another. The leads are typically Y or star connected, and the neutral is usually connected to ground or brought out with single-phase loads. As the rotor spins, 3 separate voltages are created at the stator terminals. There are other considerations in the stator's armature windings to consider, such as how they are wound, how many coils per group, as well as span and pitch. The frequency of a generator is directly related to the number of poles on the rotor and the speed of which it spins. For example, for a 4-pole rotor to rotate at 60 Hertz, it would have to spin 5 times faster than a 20-pole rotor, putting much more mechanical stress on the generator. Salient pole machines may have 10 to 20 poles, reducing the stress on these generators, but again, run at a lower RPM. Power plants may choose a rotor with a certain number of poles depending on the speed needed for the application. In other words, if the device that will be spinning the rotor, known as the prime mover, has a certain operating speed, the rotor can be selected based off of that RPM. Even with large fluctuations in load, large utility generators don't allow the frequency to change much because they are large rotating masses and provide significant inertia to the grid. This is extremely beneficial to the grid by stabilizing the voltage, but it could take up to a minute for these units to get frequency back to the proper level if something catastrophic happens because they are so large. Some widespread blackouts have been related to significant frequency changes in the response of large generators and groups of generators. Wind and solar have a much faster frequency response due to the use of electronics, but they don't provide as much grid stability provided by large generators with rotating inertia. For large systems, generators are paralleled with each other to provide more capacity to feed loads, and they must be synchronized with each other. The objective of synchronization is to match speed and phase position, so there is little or no transfer of energy when paralleling multiple units or connecting to an existing grid, or bad things could happen. Synchronizing requires matching voltage magnitudes, frequency, and phase angle. On systems with commercial or industrial generators, synchronizing these generators requires a special transfer switch with that capability. AC generators have a lot of moving parts, but the main power-producing component is the prime mover. The most common prime mover is a steam turbine or turbo machine. It consists of at least one moving part called a rotor assembly, which is a shaft or drum with blades attached and is used in thermal power plants. This part makes the rotor spin at the desired speed by using mechanical gears. Governors on the prime mover system are used to control the speed of the prime mover, which then controls the speed of the rotor inside of the generator. Most of the generation today is still being produced by burning of fossil fuels, with coal being the primary fuel of choice, but in the United States, natural gas has recently become the leading fuel over coal. When fossil fuels are burned, they create heat that boils water in a boiler, producing steam sending it to the condensing turbines, and then exhaust that steam to a condenser. The exhausted steam is the white smoke that you would see coming out of cooling towers at a generation station, and it is of no danger to the environment. The steam turbine is a form of heat engine that extracts the thermal energy from the pressurized steam and uses it to do mechanical work on a rotating output shaft. This ultimately spins the rotor of the generator. Not all fossil fuels are used to heat water to produce steam. Natural gas power plants can also burn natural gas mixed with a stream of air, which combusts and expands through a gas turbine to spin as its primary mover. Nuclear power plants are another type of generation source that provides a very large amount of power and about 11% of the world's electricity. In the United States, it provides around 20% of the electricity used, which is behind natural gas and coal, and slightly more than renewables. These plants operate in a similar fashion as fossil fuel plants by heating water to produce steam, except they don't burn fuels to create heat. Nuclear power plants get their heat from a chemical reaction where in the core of the nuclear reactor, the fission of uranium atoms releases energy that heats the water to about 520 degrees Fahrenheit. Renewables are making a large impact with power production in the world and accounting for about a third of the world's generation. The most significant are wind, solar, and hydro. Hydropower, or hydroelectricity, is by far the largest form of renewable energy and produces about 24% of the world's electricity. In the United States, there are more than 2,000 hydropower plants in operation and account for around 7% of the total energy. The most well-known hydropower plant in the United States is the Hoover Dam, and it has a total of 17 generators, each able to generate up to 133 megawatts with a total capacity of 2,074 megawatts. The power plant with the largest available capacity in the world is the Three Gorges Dam in China, which utilizes 32 turbines, each with a capacity of 700 megawatts and 2 additional 50 megawatt turbines. That's an overall capacity of 22,500 megawatts. To put that in perspective, that is more than double the amount being produced by the largest nuclear power plant in the world, which is almost 7,500 megawatts. Hydroelectric plants generate electricity like fossil fuels and nuclear power plants, but spin a turbine using the force of water instead of steam. A hydro plant uses the pressure of water created by either a difference of elevation for dams or the force of water in rivers. In either case, the head pressure can be regulated by a control gate, so when the water flows down a controlled pipeline called a penstock, the pressure builds up, spinning a turbine at the bottom and turns the rotor of an AC generator. Wind power is the next highest producing renewable behind hydropower at 6% of the United States total generation. Wind generation is continuing to rise as more of an effort goes into the production of renewable energy. Wind generation relies on the spinning of a wind turbine that turns the rotor of a generator. This type of generation can be done for individual homes all the way up to utility scale applications that are generally many units connected together as a wind farm. Typically, utility scale windmills in the United States produce about 1,500 kilowatts each and have blades that are about 80 feet long. Our current wind power capacity in the US is around 82,000 megawatts, second only to China and the European Union. The U.S. Department of Energy, or DOE, projects the U.S. to have 404,000 megawatts of peak wind power capacity by 2050. That will be enough to fulfill 1/3 of the power demand with all turbines at peak output if future projections are accurate. Solar power has been on a steady rise as it becomes more available and a good economic investment. There are lots of incentives in place to promote the growth of solar generation for your home or business. Solar generation is a totally different type of generation compared to all the others mentioned so far. There is no prime mover or AC generator with solar panels. Solar panels strictly rely on the solar radiation from the sun to be absorbed by photovoltaic panels to produce DC power. The DC power is then converted into AC by the use of power electronics inside an inverter. 36% of all new electricity generating capacity additions this past year are actually from solar power. Solar power has been holding quite steady since 2013 by being about 30% of all added electric power capacity in the United States year over year. Our current solar capacity is 69,000 megawatts, which is on track to double by 2024, adding over 15,000 megawatts each year. Here at the Power Systems Experience Center, we have a small wind turbine and several different solar installations to illustrate how these alternative energy solutions are viable and can be connected to your grid or microgrid. So what does Eaton have to do with generators or power generation? Eaton works closely with electric utilities and provides large medium voltage circuit breakers and switchgear for generation stations, as well as electrical equipment to support the operation of these power plants like transformers, arresters, protection systems, and more. In addition, our services team supports upgrades and reconditioning of existing switchgear and excitation systems, as many of these stations are relatively old. As some utilities are moving away from traditional coal-fired sources, they are converting some generators to synchronous condensers, utilizing much of the same hardware from these generation systems. These large rotating machines can provide or absorb reactive power, or VARs, to support the voltage and reactive power requirements of the power grid. A synchronous condenser is a DC-excited synchronous motor whose shaft is not connected to anything but spins freely. This provides stability and voltage control when needed, absorbing VARs when load is lost, or providing VARs like a capacitor when load is added to the system. Eaton's engineering services group has been very instrumental in several of these upgrades, repurposing the synchronous generators and converting them to synchronous condensers. Eaton offers two solutions: brownfield conversion, converting existing systems, as well as greenfield or new installations. These are especially important for systems where wind is a significant power generation source because of the intermittent nature of the wind. In addition to traditional power generation stations, Eaton is heavily involved in the installation and operation of renewable resources, including significant equipment and work with hydropower and solar installations. Finally, our services team is leading the way in the industry with microgrid solutions, tying it all together. Our Microgrid Energy Optimizer can take any generation source or energy storage solution and optimize resiliency and cost depending on the application. If you want to learn more about different types of power generation, how electricity is distributed after it is generated, and how it can be connected to your power system, contact us or your local Eaton representative to schedule a visit to the Power Systems Experience Center today.